Hello guys, good afternoon.
Good afternoon, sir.
Good afternoon, sir. How are you, sir?
Good afternoon.
Good afternoon, sir.
Very
Good
good
afternoon,
afternoon.
sir.
Good afternoon.
Good afternoon, sir.
How are
Good
you,
afternoon,
sir?
sir.
Good afternoon. Okay, wait for a few minutes, guys. I forgot to bring my headset. Just wait for a few minutes.
Good morning, sir. Good afternoon, sir.
Good afternoon.
Quantum
Let's
theory.
go to this video meanwhile.
Think it over. When an iron rod is heated, at first it turns red. As the temperature increases, it turns orange before turning yellow, and then white, and finally blue. Have you ever wondered why the rod does not turn yellow or orange before turning red? Why is light produced on heating solids? Let's understand this phenomenon better. In general, when radiations strike the surface of any body, a part of it gets reflected, some part of it is absorbed, and some bit of it is transmitted by the body. When solids are heated, they emit radiations of different wavelengths. For example, when iron is heated, it emits radiations and becomes dull red, which turns to deeper red with increase in temperature. On further heating, it changes color from red to orange and then to yellow, followed by white, and finally, at very high temperature, it turns blue. This shows that radiations are emitted in the order of increasing frequency. In the visible region, the frequency of red light is lower than that of blue light. On the contrary, an ideal black body is a perfect absorber and emitter of radiation. A blackened metallic surface or a hollow sphere with a small opening, blackened inside, almost behaves as a black body. The radiations that enter the small opening gets reflected within the sphere multiple times until all the energy is absorbed. Hence, a black body is a perfect absorber and emitter of radiant energy. It is to be noted that at a given temperature, a black body radiates maximum amount of energy. it further radiates the same amount of energy it has absorbed. Now, let's take a closer look at the graph plotted between the wavelength and intensity of the emitted radiation. The graph clearly shows that at a given temperature, the intensity of emitted radiation increases with decrease in wavelength. The intensity reaches a maximum value at a particular wavelength and then starts decreasing with decrease in wavelength. At a given temperature, there is a particular wavelength at which the radiation emitted has maximum intensity. With decrease in temperature, the position of this maximum intensity shifts towards higher wavelengths. Electromagnetic wave theory of light could not explain these observations. Max Planck then proposed the quantum theory in 1900 to explain this phenomenon. Postulates of quantum theory. According to the quantum theory, radiant energy is emitted or absorbed not continuously but discontinuously in the form of discrete packets or bundles of energy called quanta. Atoms and molecules can emit or absorb energy in discrete quantities only. The smallest amount of energy that can be emitted or absorbed is in the form of electromagnetic radiation and is known as quantum. In case of light, the quantum of energy is called photon. The amount of energy associated with the quantum of radiation is proportional to the frequency nu of the light, which implies that E is directly proportional to nu, or E is equal to h nu, where E stands for the energy of radiation, h is Planck's constant. The value of Planck's constant in SI system is 6.626 into 10 raised to the power of minus 34 joules second. In the CGS system, it is equal to 6.626 into 10 raised to the power of minus 27 erg second. In terms of velocity and wavelength, energy can be expressed as E equals to h c by lambda, as nu is equal to c by lambda. The total amount of energy absorbed or emitted by a body will be a whole number multiple of the quantum. That is, E equals to nh nu, or E equals to n into hc by lambda, where n is an integer with values 1, 2, 3 and so on. This implies that a body can only emit or absorb energy equal to an integral multiple of h nu, such as 1h nu, 2h nu, 3h nu, etc. It cannot emit or absorb energy which is a fractional value of h nu, such as 1.6h nu or 3.2h nu. This implies that energy can be emitted or absorbed as 1h nu, 2h nu, 3h nu, and so on. This is known as quantization of energy. Let's summarize. Energy is emitted in the increasing order of their frequency. A black body is a perfect absorber and emitter of radiant energy. According to Planck's quantum theory, energy is emitted or absorbed discontinuously in the form small packets of energy called quanta. The energy of quanta E equals to nh nu, and this energy is quantized.
Excuse me, sir.
Yeah.
Sir, I have a doubt from the video. I mean,
Yes.
sir, what is quantum, the smallest light that can be emitted, sir?
1 second.
Okay.
Yeah. So first, wait for a second. So most of the points we discussed about Planck's quantum theory yesterday. And if you understand,
Sir, your voice is not audible.
hello?
Sir, you are now
Your
audible.
voice is not clear, sir.
Yes, sir, it's not clear.
Your
Can you hear me now?
voice is not clear, sir.
Yes, sir.
Hello, can you hear me now? Is it clear?
Yes, sir,
Yes,
now
sir.
it's okay.
Yes, sir.
Okay. Okay. So most of the content that we went through Max Planck's quantum theory yesterday, the most of the stuff is shown in that animation video. So let's go through that video once again slowly, and I'll try to explain the points if something was not covered yesterday. Okay? As well as
Okay, sir.
when the video is going on,
Yes,
suppose
sir.
if you don't understand any point, you can raise your doubt there itself. I'll explain. Okay?
Okay, sir.
Okay, sir.
Sir, the video is not presented.
1 second, 1 second.
Okay.
Think it over. When an iron rod is heated, at first it turns red. As the temperature increases, it turns orange before turning yellow, and then white, and finally blue. Have you ever wondered why the rod does not turn yellow or orange before turning red? Why is light produced on heating solids? Let's understand this phenomenon better. In general, when radiations strike the surface of any body, a part of it gets reflected, some part of it is absorbed, and some bit of it is transmitted by the body. When solids are heated, they emit radiations of different wavelengths. For example, when iron is heated, it emits radiations and becomes dull red, which turns to deeper red with increase in temperature. On further heating, it changes color from red to orange and then to yellow, followed by white, and finally, at very high temperature, it turns blue. This shows that radiations are emitted in the order of increasing frequency. In the visible region, the frequency of red light is lower than that of blue light. On the contrary, an ideal black body is a perfect absorber and emitter of radiation.
Sir,
Blackened metallic
sir,
surface
doubt,
or a
sir.
Yes, what's your doubt?
Sir, I can't understand before one, sir. That wavelength and frequency.
This one?
Yes, sir.
Okay, see, here it is the data given. Do you remember I explained about all types of electromagnetic radiation like cosmic rays, gamma rays, X-rays,
Yes.
ultraviolet. Right. So he specifically took only visible range from red to violet. Okay. Out of all, so when you look at the VIBGYOR, VIBGYOR, which is highly energetic, which
Red.
radiation is highly?
Red.
No, it is
Red,
violet.
sir.
I said very clearly in the last class.
Violet, sir.
Violet, high frequency range, sir.
High
Violet, sir.
frequency, high energy, high
Sir,
wave
can you
number.
please repeat your question?
Which is more energetic radiation out of all VIBGYOR?
Okay, sir.
It is violet. Okay.
Yes.
Therefore, its frequency is also more for violet rather than red. But wavelength is quite reverse, right? Because energy and wavelength quite inversely proportional.
sir.
Like I showed yesterday derivation as well. So that when you compare violet and red, more energetic radiation is violet, whereas more wavelength is associated with red light. Yes or no?
Yes.
Yeah.
Yes,
Any more doubts in it? Any more doubts? Okay, shall we proceed?
Yes, sir.
Yes.
Yes, sir.
Frequency of red light is lower than that of blue light. On the contrary, an ideal black body is a perfect absorber and emitter of radiation. A blackened metallic surface or a hollow sphere with a small opening, blackened inside, almost behaves as a black body. The radiations that enter the small opening gets reflected within the sphere multiple times until all the energy is absorbed. Hence, a black body is a perfect absorber and emitter of radiant energy. It is to be noted that at a given temperature, a black body radiates maximum amount of energy. It further radiates the same amount of energy it has absorbed.
Guys, this is notable point and this is important.
Same amount of energy it has absorbed. Maximum amount of energy. It further radiates the same. It is to be noted that at a given temperature, a black body radiates maximum amount of energy. It further radiates.
You can note down this point. This is a property of a black body. At a particular temperature, a black body radiates the maximum amount of energy. What does it mean? Guys, can anyone explain? What is the meaning of this statement?
Sir, at a particular temperature, sir, the
Okay.
black body is able to radiate the maximum amount of energy.
What does it mean?
The energy which is absorbed is the same amount of energy is also released, sir.
Okay. Any other meanings?
When it 100 amount of radiation coming means it will release 100 radiation, sir.
Okay. See, here it means, see, suppose when you're taking two different bodies, one is black body, other one is any ordinary substance. If both black body as well as ordinary substance, if both get heated and both are heated to the same temperature, suppose black body is heated up to 100 degrees Celsius, even ordinary substance is also heated up to 100 degrees Celsius. Therefore, both are kept under the same temperature. Now, under that 100 degrees Celsius temperature, black body emits one kind of radiations, right? So that those emitted radiations are associated with some amount of energy. Let it be some 100 calories. Next, at the same 100 degrees Celsius, the other ordinary substance that would also emit energy, yes or no, in the form of light. But that cannot emit energy equivalent to the energy emitted by black body. As I said, if black body is emitting 100 calories of energy at 100 degrees Celsius, at the same 100 degrees Celsius, the other substance may emit energy which is less than 100 calories. Understand? Hello guys.
Yes, sir.
So that,
Sir, please once again explain
Yes,
this.
sir.
that
Once
point,
again,
sir.
repeat the points.
okay, right. Suppose this is a black body, this is ordinary substance, this is black body, this is ordinary substance. So both substances are supplied heat energy. You are giving heat. So by the supplying of heat, let's say the temperature of black body reaches 100 degrees Celsius. Even ordinary substance temperature also reaches 100 degrees Celsius. Then what will happen? This black body must emit energy, right, in the form of light again. It should radiate energy.
Yes,
It
sir.
will also radiate energy. Suppose if black body emits some 100 calories of energy at this temperature, this ordinary substance at the same temperature, it cannot exist 100 calories. It cannot. It should be definitely less than 100 calories. Okay? Getting my point?
Sir, no other substance can emit more than the black body, sir.
Very good. No other substance can emit energy more than as well as not even equal to black body radiation. That is the meaning of that statement. Okay?
Okay, sir.
Fine. So I'll get back to the video. So listen that once look at that statement. At a given temperature, a black body radiates the maximum amount of energy. So maximum amount of energy can be irradiated only by black body, no other body. That is the meaning of this statement. Understand?
Okay.
Yeah.
Radiates the same amount of energy it has absorbed. Now, let's take a closer look at the graph plotted between the wavelength and intensity of the emitted radiation. The graph clearly
See guys, I explained this graph in quite reverse way yesterday. Anyhow, you can understand in any way. Nothing wrong with it. Okay. So he is taking the graph from right to left, correct? From this in this way. Can you see this cursor?
Yes, sir.
From the value of around
Yes.
14,000 nanometers to 12,000 to 10,000, 8,000. So he is taking in the decreasing order of wavelength from right to left. But I explained from in increasing order of wavelength. Do you remember yesterday? You can
Yes,
understand.
sir.
Both ways are correct. Both ways are right. So according to him, see, there are two different curves taken. One is green curve, which is at a particular temperature T1. At a particular temperature, when a substance is a black body kind of substance, when a substance gets heated, what happens? It emits radiation. So that radiation, nothing but light. So that light is associated with some wavelength. So as a function of wavelength, how the intensity varies. So on vertical axis, intensity is taken. Suppose at this particular temperature T1, imagine, look at the green curve. At this particular temperature T1, you are not changing temperature. See, temperature remains constant. At that particular temperature, it is noticed that this is the value of intensity with a frequency around 15,000, right? And this is the intensity noticed. Maybe this is the value, which is far much less than 0.5. Maybe it is 0.1. And the other observation is made. Suppose that 12,000 nanometers of wavelength of a same electromagnetic radiation, maybe this is the intensity little more than 0.1. Like that, if the value is decreased further up to 8,000 nanometers, at 8,000 nanometers of wavelength of a same electromagnetic radiation, the intensity was observed, it is around 0.2. Similarly, as further wavelength is reduced, it is noticed. This is the point where 6,000 nanometers is the wavelength. At that wavelength, this is the intensity 0.5. This is at this particular temperature, and the same experiment is carried out at some more temperature. Maybe at some more temperature. This is T2. Therefore, T2 is higher than T1. You have taken to conduct that experiment. So at some other higher temperature, it is noticed that if you compare, if temperature is increased, see, compare the point on the green curve as well as red curve. At the same wavelength, intensity is a bit more upon the red curve, yes or no?
Yes, sir.
And if you further reduce the wavelength, suppose come to this point, let it be 10,000 nanometers, let it be. So the same light at temperature T1 is showing this is the wave, this is the intensity, right? Maybe around 0.2. Whereas under the same wavelength, that on the red curve, the intensity is showing a bit more. This is the value around 0.3 or 0.4 approximately. And at this 6,000 nanometers, the same radiation at temperature T1, it shows intensity 0.5, whereas on the red curve, it shows pretty much higher than 0.8. Understand? Therefore, the same electromagnetic radiation within the range of certain value of wavelengths, maybe from 2000 nanometers to 14,000 nanometers, same light, but their intensities are changing as a function of temperature. If temperature is changed, intensity values are also changing for the same electromagnetic radiation. Understand?
Yes,
Hello
sir.
guys.
Excuse me, sir.
Yes.
Can you repeat this once again?
Which point don't you understand?
So, how it is changing with the function of temperature?
It is changing, right? Suppose if you take up at a particular value, let's say 6,000 nanometers. At 6,000 nanometer, one light, at temperature T1, it is showing 0.5 as the intensity. Yes or no?
Yes, sir.
Under the same 6,000 nanometers, if you check the point on the red curve, so the corresponding intensity will be like this value, right? Which is definitely more than 0.5.
Yes, sir.
So the intensity value is changing from 0.5 to around 0.8 when you change the temperature from T1 to T2, yes or no?
Yes, sir.
Now, can you not generalize as a function of temperature, intensity of the electromagnetic radiation is changing?
Yes, sir.
Okay.
Thank you, sir.
Shows that at a given temperature, the intensity of emitted radiation increases with decrease in wavelength.
Okay. So this is also important point.
Intensity of emitted radiation increases with
See, at a given temperature, the intensity of the emitted radiation increases with decrease in wavelength, right? So he is explaining in a reverse way. See, when you look at the curve, suppose you look at the green curve or even red curve, any curve. Let's take up green curve. As the wavelength is decreasing, but the intensity is increasing, right? Therefore, you can tell that at a particular temperature T1, at a given temperature T1, the intensity of the emitted radiation increases with decrease in wavelength, right?
Yes,
You
sir.
should note it down, this point. Yeah.
decrease in wavelength. the intensity reaches a maximum value at a particular wavelength and then starts decreasing with decrease in wavelength.
See, look at this point again. This is important. So it reaches a maximum value. When you look at it, see, when you look at the green curve, as wavelength is decreasing, intensity is continuously increasing and reaching a maximum point. So that at that maximum point, the wavelength is known as lambda max. Do you remember? Yesterday I wrote lambda max.
Yes, sir.
Yeah, and thereafter again the value is decreasing, right? Intensity is decreasing, with further decrease in wavelengths. Do you understand the statement? So this is same observation even for the red curve, even at some other temperature T2. So that this is one curve, green curve, which is noticed for a particular radiation at temperature T1. To the same radiation, the second curve is drawn at higher temperature. Therefore, when you change the temperature, the intensity of that particular radiation will also be changed as a function of wavelength. Okay.
At a given temperature, there is a particular wavelength at which the radiation emitted has maximum.
See, at a given temperature, there is a wavelength at which maximum intensity of radiation is noticed. This is, suppose at a given temperature T1. When you look at the entire green curve, where did you notice the maximum intensity? This is the point. Hello?
5,000.
Yeah, approximately 5,000. So at a given temperature, there is a wavelength at which maximum intensity of radiation is emitted, known as lambda max. And at higher temperature T2, this is the maximum intensity, right? And when you look at its lambda max, it is close to some 4,000, right? Whereas at T1, it is close to 5,000. It is close to 5,000. Therefore, can you not generalize when you increase the temperature from T1 to T2? The lambda max is shifting towards 4,000 from 5,000, which was the previous case at T1, right?
Yes,
Understand?
Yes, sir.
Intensity. With decrease in temperature, the position of this maximum intensity shifts towards higher wavelengths.
So he told in a reverse way.
Electromagnetic wave theory.
He told in a reverse way. If you understand, both mean same. So I said, if you increase the temperature from T1 to T2, lambda max is shifted from 5,000 to 4,000. That means higher wavelength to lower wavelength. What he said, if you reduce the temperature from T2 to T1, then what is happening? Lambda max is shifting from 4,000 to 5,000. Both mean same, yes or no?
Yes, sir.
Yes.
Right.
Decrease in temperature, the position of this maximum intensity shifts towards higher wavelengths.
Sir, please stop the
Sure.
sir.
Sir. Yeah. Completed?
Completed, sir.
Electromagnetic wave theory of light could not explain these observations. Max Planck then proposed the quantum theory in 1900 to explain this phenomenon. Postulates of quantum theory. According to the quantum theory, radiant energy is emitted or absorbed not continuously but discontinuously in the form of discrete packets or bundles of energy called quanta.
See, this is very nice information. So as you know, radiant energy is emitted. Radiant energy is emitted. Suppose, black body emits radiation, right? So he's speaking about that kind of radiant energy emission. So radiant energy is emitted or absorbed not continuously, but it is discontinuously, which are known as discrete. I explained about discrete word yesterday. Do you remember?
Yes, sir.
Yeah. So
Yes, sir.
discontinuously in the form of discrete small energy packets or bundles of energy known as quanta. We discussed about this. So that, see, you can see when you look at this diagram in this video, this is taken as a small energy packet. This is another energy packet. Like that, collection of all this kind of small energy packets together give you the light, stream of particles, stream of quanta. Understand? Quanta is a plural word. Combination of quantums. Quantum is a singular word. Combination of many quantums will give you quanta.
Atoms and molecules can emit or absorb energy in discrete quantities only.
See, you should whether you noticed or not. So observe this video once again. So look at it. When you look at, see, this green color particle, basically it is an electron. Of course, it is not related to this concept, but yes, this will help you to understand even Bohr's theory. Okay, because here there is a word we have seen, that is quanta. Quanta is a word. The same word was utilized even by Niels Bohr. So you must understand what I mean by quanta here. So related to that word quanta, this video will help you a lot. So when you look at it, so imagine this red color particle is a nucleus. Around the nucleus there are circular paths. This is orbit number 1. The next one is orbit number 2. So here the electron is revolving in the second orbit, right? Yes, sir.
Yes, sir.
Yes, sir.
Now let's see what happens next.
Can emit or absorb energy in discrete quantities only.
See, now what happened? A light has
It
come.
moved to third orbit, sir.
Yes, it moved to third orbit. A light has come, and that light was absorbed by that electron and jumped into the third orbit. Yes, sir.
Yes, sir.
This idea will help you when we discuss Bohr's model. And what did you notice now?
Sir, when the light leaves, it is radiated back, then the electron moves through the same place, sir.
Yes, electron is coming back from third orbit to second orbit, if you notice. When it is coming back from third to second, it irradiates. That electron is releasing energy in the form of light. Light went away. Have you noticed?
Yes, sir.
That quanta, that light was, whether you noticed or not, even that light, that releasing of light was, let's see, clearly notice in which form that light is being emitted. Clearly notice. See, have you noticed that? That blue color that was indicated, that was, whether you noticed or not, that light was, see, just look at the shape of that light. It looks like a quanta, right? That's how he showed over here.
Yes, sir.
Yeah, like this, right? Like quanta.
Yes, sir.
Right.
Sir. The smallest amount of energy that can be emitted or absorbed is in the form of electromagnetic radiation and is known as quantum.
See, note it down. This is important point. The smallest amount of energy that can be emitted or absorbed is in the form of electromagnetic radiation, and that smallest amount of energy is known as quantum. Okay. How that quantum looks? It is a rough diagram. This is the most important consideration from Planck's quantum theory. Just note it down. Very beautiful video. All the important information is given without any unnecessary stuff.
Yes.
Completed?
Yes, sir.
Yes, sir.
In case of light, the quantum of energy is called photon. The amount of energy associated with the quantum of radiation
See guys,
is
this is another name of photon. Photon, nothing but it is the energy. It is particularly photon is the energy packet of light energy, particularly light energy. Okay, so quanta can be energy forms of any small energy packets of any mode of energy. But if you are talking about energy packets of only light energy, then they are particularly called photons. Understand? So quanta has a broad meaning. Quanta nothing but energy packets of any form of energies, including light energy. If you want to speak particularly about energy packets of a light, you can call it as quanta, nothing wrong with it. But there is a specific word for it that is known as photon. Understand?
Yes,
Yes, sir.
Yeah, photon is indirectly another name for quanta of light. 1 second, guys. Somebody's coming. Hello, guys. Can you hear me?
Yes, sir.
yes, sir.
Yeah.
proportional to the frequency nu of the light, which implies
Of
that
course,
E is directly proportional
So
to
here
nu.
onwards, all the stuff what is going to written over there, you guys know about it, right? We discussed even more detail than this.
Or E is equal to h nu, where E stands for the energy of radiation, h is Planck's constant. The value of Planck's constant in SI system is 6.626 into 10 raised to the power of minus 34 joules second. In the CGS system, it is equal to 6.626 into 10 raised to the power of minus 27 erg second. In terms of velocity and wavelength, energy can be expressed as E equals to hc by lambda, as nu is equal to c by lambda. The total amount of energy absorbed or emitted by a body will be a whole number multiple of the quantum.
Guys, just note it down. What does it mean? E is equal to n times of h nu, right?
Sir.
So
Yes.
here whole number nothing but that n. Whole number is speaking about what? That n. N is speaking about what? How many energy packets? Correct? Number of photons. Yes or no?
Yes.
So note it down. This statement is. So below that statement, write down, therefore E is equal to n times of h nu.
That is E equals to nh nu, or E equals to n into hc by lambda, where n is an integer with values 1, 2, 3 and so on. This implies that a body can only emit or absorb energy equal to an integral multiple of h nu, such as 1.
This is very important statement. Note down. The total amount of energy absorbed or emitted by a body will be a whole number of multiples of quantum. First note down, I'll explain. This statement again will help you a lot to understand Bohr's model. So Niels Bohr utilized Planck's quantum theory a lot to explain his atomic model.
sir.
Completed? Okay. So I read that
No,
the total
sir.
amount of,
Please wait.
yes, proceed.
Completed, sir.
Okay. So the total amount of energy absorbed or emitted by a body will be a whole number of multiples of quantum. Suppose if E is the total amount of energy emitted or absorbed by a body, maybe a black body. This must be equal to a whole number of multiple times of quantum. Quantum nothing but E, h nu, right? Because h nu is speaking about energy of each and every energy packet, each and every photon. It is a whole number. This n is always whole number, either 1 or 2 or 3 and so on up to infinite. It can be, right? Of course, infinity is, it doesn't make any sense. 1, 2, 3, 4, but it should not be 1.1, 1.5, 2.6 or any fractional value. No. So what is the difference between this and this? It must be the whole number of multiple, the total energy of the total energy of that irradiated light by that black body must be whole number of multiple of this quantum. This is a statement given by Max Planck. Suppose if fractional values are allowed, after 1 there can be 1.00001, and after 1.0001 there can be 1.00002 and so on. So between 1 and 2 you can get infinite possible numbers, right?
Yes, sir.
Yes.
What it indicates between 1 and 2 there is a continuity. So energy liberation is continued, which indicates the wave character. So listen carefully. Suppose if fractional values are allowed, suppose if this n is even a fractional number, then the total energy need not to be whole number of multiples of quantum. Need not to be. Suppose if it is true, if n allows even all values, not only whole numbers, in that case, for a particular energy 1 times of h nu, the next possible energy must be 1.000001 times of h nu, and next possible energy must be 1.000002 times of h nu, like that. What does it mean? Between one energy to next energy there is a continuity. Take the other point, other possibility. The other possibility is that after 1 only 2 is feasible, between 1 and 2 nothing else is possible. After 1 the next whole number 2 only permitted. Therefore between 1 and 2 there is a gap, no? Hello? Isn't it discrete? 1 and 2 are discrete energy levels, no?
Yes, sir.
1 times of h nu, 2 times of h nu, both are discrete energy levels. They are not continuous. That's what Planck assumed. Energies are emitted or absorbed by the object discontinuously. Therefore, after 1 into h nu, there must be 2 into h nu, but not 1.5, 1.6, 1.8, and so on. Get my point? Hello?
Yes, sir.
Right.
Yes, sir.
This point will help you a lot when we go through
Yes.
Bohr's atomic model. Again, anyhow, I'll discuss continuity to this point over there.
1h nu, 2h nu, 3h nu, etc. It
You
cannot emit or
note
absorb.
down. You can note down E values possible 1 h nu, 2 h nu, 3 h nu, and so on, but not 1.5 h nu, 1.6 h nu, 2.6 h nu. They're not possible.
Energy, which is a fractional value of h nu, such as 1.6 h nu or 3.2 h nu.
They're not possible.
This implies that energy can be emitted or absorbed as 1 h nu, 2 h nu, 3 h nu, and so on.
So this is known as quantization of energy. This word is very important. See guys, after 1 h nu, the next possible energy is what?
2h.
After 2h nu?
2h nu, sir. 2h nu.
In whole number.
Yes.
Always
Yes.
it will be a whole number, sir.
Yes. Therefore, this is known as this particular sequence. No, here energies are following a particular sequence. After 1, there is only 2. After 2h nu, there is only 3h nu. So here the energy values are following a particular sequence. This is known as quantization of energy. This is known as quantization of energy. Quantization of energy means energy is not continued, it is discontinuous. Energy is emitted in a discrete manner of small energy packets. Understand my point? I repeat once again. Energy is not continuous. Energy is emitted or absorbed discontinuously. Energy is not continuous. Energy is either emitted or absorbed discontinuously in the form of small or in the form of discrete small energy packets. In the form of discrete small energy packets. This is known as quantization of energy. This is known as quantization of energy. Okay. So this quantization of energy word will help you. Yeah.
Sir, discontinuously in the form of?
In the form of discrete, D-I-S-C-R-E-T-E, discrete, in the form of discrete small energy packets, known as quantization of energy. So this quantization of, this quantization of energy, this word is quite useful in Bohr's model. Niels Bohr took this assumption to explain his atomic model from Planck's quantum theory.
This is known as quantization of energy. Let's summarize. Energy is emitted in the increasing order of their frequency. A black body is a perfect absorber and emitter of radiant energy. According
See here, there is important point.
absorber and emitter of radiant energy. According to Planck's quantum theory, energy is emitted in the increasing order of their frequency.
See, he is saying one important point. So when a black body when black body or any metal body starts irradiating, first which color do you notice? Is that red or directly blue?
Red, sir.
Red, sir.
First red. And after red, you will notice a kind of orange. After orange, you will notice a kind of white.
Orange.
After white, you will notice a kind of blue, right? So in
Yes,
different
sir.
stages, ultimately you will
Yes, sir.
you will notice blue radiation emission. Now, can you not generalize that? As temperature is increasing, or when black body radiation starts emitted, you will notice releasing of electromagnetic radiations from lower energy to higher energy, because red is lower energetic radiation, blue is higher energetic radiation. Yes or no?
Yes, sir.
It emits radiation from lower energy or lower frequency to higher frequency, right? From red to blue. Important point. See, I'll show you that
Let's
point once again.
summarize. Energy is emitted in the increasing order of their frequency.
So energy is emitted in the order of the increasing frequencies. Energy is emitted in the order of their increasing frequencies. Do you understand this point meaning? Hello?
Yes, sir.
Yeah, you can note down that point. Energies are emitted in the increasing order of their frequencies during the emission of black body radiation.
A black body is a perfect absorber and emitter of radiant energy. According to Planck's quantum theory, energy is emitted or absorbed discontinuously in the form small packets of energy called quanta. The energy of quanta E equals to nh nu, and this energy is quantized.
So hope you understand most of the stuff given in this video. Okay.
Oh, yes, sir.
Now what I recommend you people, almost time is over. Let's do one thing. Now you can go through each and every point given in the textbook about Planck's quantum theory once again, even today.
Okay, sir.
Now I hope you would understand even better than yesterday when you tried to go through the textbook. Okay.
Yes, sir.
And still, if you
Yes,
find any
sir.
point difficult, bring to my notice tomorrow. Tomorrow we'll discuss. So tomorrow we are going to complete this Planck's quantum theory. Fine.
Okay, sir.
And after that we will
Yes,
discuss
sir.
Einstein's photoelectric effect. Okay, guys. Have a good day. See you tomorrow.
Thank you, sir.
Thank you,
Have
sir.
a
Have a nice day, sir.
Thank you.
Thank you.
Thank you, sir. Have a nice day, sir.
Thank you, sir. Have a nice day, sir.
Thank you.
Thank you, sir.
Okay, guys. Bye.